Hello, welcome back to another video. Today we're going to be doing topic 1.7, rational functions and end behavior. So today we're finally starting rational functions. You'll be hearing about rational functions for lesson 7, 8, 9, 10, and 11. Okay, so this is just the beginning. We're going to be doing the end behavior. A rational function is simply the quotient or the fraction of two polynomials. Okay, so remember in the last lesson that we did, we defined a polynomial as an expression that has exponents that are only positive integers and that they're combined with either multiplication, addition, or subtraction. Okay, and remember we had excluded division because when you're dividing, that's actually going to become a rational function. So a rational function has y equals f of x divided by g of x, where both f of x and g of x are polynomials. It also says that g of x, which is in the denominator, cannot equal 0. The reason it can equal 0 is because anything divided by 0 becomes undefined. Okay, let me give you an example. Let's go to the calculator. If I say, let's see, some crazy number divided by 0, it's going to be undefined. If I do, 9 divided by 0, it's undefined. Let's say I do x divided by 0, it'll be undefined. Okay, so you can have 0 in the denominator, and in a few lessons, we're going to talk about how anything that equals 0, factors that equal 0 in the denominator actually create vertical asymptotes in rational functions. Okay, so let's go back over here. So the following are all examples of rational functions. So notice that the key here is that all of the denominators have at least one x. So that's how you know whether you're looking at a rational function. Now the numerator does not necessarily need an x. So this 2 here doesn't have an x. There's an imaginary x to the power of 0 here. So remember that anything that is raised to the power of 0 always equals 1. So x to the power of 0 equals 1. So this is really 2 times 1, which is equal to 2, which is what we started with. So at first, all we had was 2. But because today's lesson, you're going to want to know what the degree is, it is helpful to know that all whole numbers are multiplied by an imaginary x to the power of 0. And then at the denominator, if you have x to the power of 1, that's the same thing as saying x. So this is raised to the power of 1. And yeah, so if, for example, I tell you 5x cubed plus 10, and then this is divided by 2, that would not be a rational function because there is no variable in the denominator. If I put 2x, then yes, but if it was just 2, it would not be a rational function. Okay, so let's talk about end behavior. In lesson 6, we did end behavior of polynomial functions, and that was when we did the right side first, and we looked at the leading coefficient, if it was positive or negative, determined if the right side went up or down to positive or negative infinity, and then if your degree was even or odd, determined if the left side matched the right or if it was opposite of the right. Okay, so today will be a little bit different because we're not just dealing with one polynomial, but rather the division of two polynomials. So there's 3 different cases. Here we have f of x, and just as an example, we have a times x to the power of n divided by b times x to the power of d. Okay, so a and b here are going to be your leading coefficients for the numerator and the denominator, and then n and d are your degrees. Another word for degree is exponent. Okay, so case 1 is that the leading terms have the same degree. I'm going to give you some acronyms that sound kind of crazy, but I hope that they help you remember what the cases are. Okay, so the first acronym is EATS DC. That stands for exponents are the same. You're going to divide the coefficients. Okay, so for this case, you do have a horizontal asymptote, and the equation of that asymptote is y equals a divided by b. So in this case, let's say that the degrees were both to the power of 3, then all you would do is grab the leading coefficients and divide them. Okay, So for example, if we had 7x squared divided by 8x squared, the horizontal asymptote would be at 7/8. Okay? Don't forget the y equals. The y equals is very, very crucial. If on the AP test you do not put the y equals, it will be marked wrong. Okay? The y equals is important because that lets the reader know that this is a horizontal line. If you have x equals a number, then it'll be a vertical line. And we're going to do vertical asymptotes soon. So you need to know that y equals is for a horizontal asymptote and x equals will be for a vertical asymptote. So if as your teacher or as an AP reader, you don't specify y equals or x equals, a number in and of itself will be marked wrong. It has to be the equation of the line that represents the horizontal asymptote. Okay? Case 2 is that the denominator dominates the numerator. My acronym for this is BOBO. That stands for bigger on bottom, and the last O stands for y equals 0. Okay, so bigger on bottom, 0. This one is easy. Okay, this one does have a horizontal asymptote, and you don't have to do any other math other than say it's at y equals 0. Okay, so for example, if I tell you 5x to the power of 3 divided by 10x squared, oh, I did this wrong. Sorry. Well, let's say 24 to the power of 24. Okay, so the 24 is bigger in the bottom, so this would be y equals 0. You would box that in and move on. Okay. The last case is a little bit different. That's when the numerator dominates the denominator. My acronym for this is BOTN. That stands for bigger on top, no horizontal asymptote, none. Bigger on top, none. This is the only case where you have no horizontal asymptote. Okay, so for case 1 and case 2, you do have a horizontal asymptote, but for case 3, you do not have a horizontal asymptote. Now, you could have what is called a slant or an oblique asymptote. That happens if and only if the degree of the numerator is exactly one more than the degree of the denominator. Okay, now in Algebra 2, you should have learned how to do polynomial long division. That looks something like this. If you do x squared plus 5 divided by x cubed plus 8x plus 10, something like that. And then you do your stuff here and you do all this other stuff. And it's like regular long division from elementary, but with variables in it. Okay, so I'm going to reteach how to do this in an upcoming video. But the process of doing long division is what gives you the equation of your slant asymptote. And again, that happens if and only if your degree in the numerator is exactly one more than the degree in the denominator. And you need to know that slant and oblique are interchangeable. They mean the same thing. That's similar to in lesson 4 when I told you that a local max was the same thing as a relative max. So the same thing. So a slant asymptote is the same thing as an oblique asymptote. Okay. Now, when we did lesson 6, we did 2 examples of rational functions and end behavior. And basically what we had determined is if you have a horizontal asymptote, let's say this one is at 2, this is straight from the notes on lesson 6. That graph looked like this. Okay. That means that your left and right limit statements are going to be the value of your horizontal asymptote. So here, as you go to the left, your y values approach 2. And as you go to the right, your y values approach 2. Okay? For case 2, if you have the horizontal asymptote at 0, and again, this is straight from the lesson 6 notes, as you go all the way to the left, you approach 0. If the horizontal asymptote is at 0, and all the way to the right, you approach 0 because the horizontal asymptote is at 0. So for case 1 and 2, when you write your left and right limit statements, your answers will be the exact number of the horizontal asymptote. For case 3, it's a little bit different, okay, because you don't have a horizontal asymptote. What you do have is a slant asymptote, which would look like this, okay? For this case, you can either go up to positive infinity on the right and down to negative infinity on the left, or it could look like this, and on the left you go up to positive infinity, and on the right you go down to negative infinity. So for the slant asymptote, your limit statement will either be positive infinity or negative infinity. So that's the only difference from case 3. Now to figure out whether you're going to the positive or negative infinity, there's going to be 2 steps. They're similar to the steps we did in lesson 6. For step 1, you're going to divide the coefficients to do your right limit. So remember, in lesson 6, we always did the right side first. So if your coefficient is positive, you go up on the right. If your leading coefficient is negative, you go down on the right. After that, you're going to subtract your exponents to do your left limit. So remember, if your degree is even, they're the same on both sides, and if your degree is odd, it's opposite. Okay, so we'll do some examples in a little bit. Example 1, we're going to determine if the following rational functions have a horizontal asymptote, a slant asymptote, or neither. And then if it does have a horizontal asymptote, we're going to write the equation of the asymptote. Okay, so for letter A, we are trying to figure out what the leading term is. The leading term is the one with the highest exponent. Okay, the 4x doesn't have a degree, so I know it's going to have a degree of 1. And the 7, which is a whole number, doesn't have any x at all, so I know that there are 0 x's there. I could put an x to the power of 0, which equals 1. I went into detail about this on lesson 6. Okay, so of the 3 exponents, 2, 1, and 0, 2 is the biggest, so I know that the term 3x squared will be my leading term. And in the denominator, the 3 is also being multiplied by an imaginary x to the power of 0, so between the degree of 2 and 0, the term with the degree of 2 is bigger, which is 5x squared. Okay, now if I look at the degrees, I have a degree of 2 at the top and a degree of 2 in the denominator. My exponents are the same. That would be case 1, which is eats dc. Okay, exponents are the same. So there is a horizontal asymptote, and to find it, I need to divide my coefficients. So my equation will be y equals 3 divided by 5. Okay, and I'm going to box that in. That is my final answer. Let me actually just box in this instead. Okay, now if you could reduce the fraction, you would, but these numbers you can't reduce them anymore. Okay, let's do letter B. So again, the 2x has a power of 1, the 5 is multiplied by x to the power of 0. So between these two, the 2x would be the leading term. In the denominator, we have x squared. The 3x has a power of 1. The 2 has a power of 0. Of all 3, the x squared is the leading term. Okay, so I have a power of 1 in the numerator, power of 2 in the denominator. The 2 is bigger and it is at the bottom, so this will be Bobo. Bigger on bottom. This one does have a horizontal asymptote, and the equation is that y equals 0. Okay, let's do another one. 2x squared minus 4 times x to the power of 0. Of the two, 2x squared is the leading term. 5x is raised to the power of 1, and 9 is being multiplied by x to the power of 0. Of the two, 5x is bigger. Okay, if I look at my degrees, I have 2 in the numerator, 1 in the denominator. The 2 is bigger on the top, so that means this is bottom. That means that there is no horizontal asymptote. Now the question also asks, could there be a slant asymptote? Remember, for there to be a slant asymptote, your numerator has to be exactly 1 bigger. Sorry, I said that wrong. The degree of the numerator has to be exactly 1 more than the degree of the denominator. So my degree in my numerator was 2. I can subtract that from the degree of the denominator, which was 1, and that equals exactly 1. So that means that this one does have a slant asymptote. Now, this question didn't ask you to find the equation of the slant asymptote. Like I said, that'll be in a future lesson, and we'll find that by doing long division. In the future, your slant asymptote could look something like y equals 3x plus 5, and that would be your answer. But this is just an introduction, so we're not going to do that just yet. Okay, moving on to letter D, we have 4x to the power of 1 plus 5 times x to the power of 0. 4x would be the leading term. In the denominator, we have 8x to the power of 1 minus 1 times x to the power of 0. The 8x would be the leading term. I see that my degree is 1 in the numerator, 1 in the denominator. They are the same number, so if the exponents are the same, I'm going to divide the coefficients. That means I do have a horizontal asymptote, and the equation would be y equals 4 divided by 8. I could reduce that to y equals 1/2. Okay, on this one, I have 3 times x to the power of 0. That's the only term, so that would be my leading term. And in the denominator, x squared plus 3x to the power of 1 minus x to the power of 0. The biggest degree would be 2, which makes x squared my leading term. The degree is 0 in the numerator, 2 in the denominator. It's bigger on the bottom, so it is Bobo. There is a horizontal asymptote, and the equation is y equals 0. Okay. For letter F, we have negative 4 times x to the power of 0 divided by 2x to the power of 1 plus x to the power of 0. My leading term would be this one in the numerator, this one in the denominator. Degree of 0 at the top, degree of 1 at the bottom. It's bigger on the bottom, so it's Bobo. The horizontal asymptote is at y equals 0. Okay, let's go to the next page. We're going to write limit statements to describe the end behavior of the following rational functions. So remember to do the left and right limit statements of rational functions. You really just need the value of the horizontal asymptote. Okay, let me pull up the 1.6 notes just so I can show you, refer back to this, because we did 2 examples of this in the last lesson. Okay, so B and C were both rational functions. Letter B had a horizontal asymptote at y equals 2, so my answer for both the left and the right were 2. Okay, because all the way to the left we approach 2 and all the way to the right we approach 2. Same thing for this one, the horizontal asymptote was at y equals 0, so both of my answers were 0 because I move all the way to the left. I'm never going to go past 0. Okay, this line doesn't go up and the line didn't go down. It just stayed forever at 0, all the way to the left and all the way to the right. So when you're trying to figure out your limit statements to do your left and the right, all you need is to figure out what the horizontal asymptote is, because that's going to be your answer. Okay, so what we're going to do here is just repeat the process. We're going to find the horizontal asymptote and then use that value to write the limit statement. So we have 2x cubed plus 4x to the power of 1 minus 1x to the power of 0 divided by 6x cubed minus x squared plus 4 times x to the power of 0. My leading term is 2x cubed in the numerator and 6x cubed in the denominator. Because my degrees were both 3, that means the exponents are the same. So this will be e to the c. To find the horizontal asymptote, I would divide the coefficients 2 over 6, which does reduce to 1/3. For the left limit statement, you would write the limit as x approaches negative infinity, f of x equals 1/3. For the right, you write the limit as x approaches positive infinity, f of x equals 1/3. Okay, so your final answer here became your final answer for the left and the right limit statements. And remember, the left is always as x approaches negative infinity, and the right is always as x approaches positive infinity. Make sure that when you write your limit statements, you keep this part in a tight little square. Don't make your arrows too big. Don't write your limit too small like this, and then it looks like that. You don't want it to be a long rectangle. You want it to be a tight little square. Whatever this is, call it this over here as well. Okay, let's do G. 5x squared minus 8x to the power of 1 plus 9x to the power of 0 divided by 2x cubed plus x to the power of 1 minus 1 times x to the power of 0. The leading term in the numerator is 5x squared, and the denominator would be 2x cubed. I have a degree of 2 on the top, a degree of 3 at the bottom. It's bigger on the bottom, so this will be Bobo. So my horizontal asymptote will be at y equals 0. So I have the limit as x approaches negative infinity, g of x equals 0. The limit as x approaches positive infinity, g of x equals 0. Okay, let's do another one. Here we have negative 3x to the power of 4 minus x squared plus x to the power of 1 divided by x cubed plus 4x to the power of 1 plus 4x to the power of 0. The leading term would be negative 3x to the power of 4 because it has the biggest exponent, and at the denominator it would be x cubed because it has the biggest exponent. The exponent was 4 in the numerator, 3 in the denominator. I am bigger in the top, so this will be a case of bottom. Now this one does not have a horizontal asymptote, but we can follow the steps I had you write under case 3. So the first thing you're going to do is divide the coefficients to figure out if your coefficient will be positive or negative, and then subtract the exponents to see if your degree will be even or odd. Okay, so I'm going to do that here. My coefficients are negative 3 in the numerator, and there is an imaginary 1 here, so divide it by 1. And then you have x, and then subtract your exponents, 4 minus 3. Okay, that becomes y equals negative 3 times x to the power of 1. Now this will be just how we did it in lesson 6. Okay, my leading coefficient is negative, and my degree, which is 1, my degree is odd. Okay, so now we're going to write the limit statements. The limit as x approaches negative infinity, h of x equals, and I'll write the answer in a minute. I'm just setting up the problem. For the left side, the right side, the limit as x approaches positive infinity, and then h of x equals. Okay, now remember in lesson 6, we said you always start with the right side, and that comes from your leading coefficient. If your leading coefficient is negative, you go down to negative infinity on the right. For the left side, you look at the degree. Because the degree is odd, that means it'll be opposite of what you had on the right. So this is going up to positive infinity. Okay, let's do some examples with the graph. Graphically, it's a lot easier because all you need to do is locate the horizontal asymptote. I see that there's a horizontal asymptote right here. So I'm going to label that horizontal asymptote at y equals positive 2. Okay, so my answer will read the limit as x approaches negative infinity, f of x equals 2. The limit as x approaches positive infinity, f of x equals 2. Okay, for letter E, I see the horizontal asymptote right here. Now you don't want to confuse it with the vertical asymptotes. We'll get to that eventually, but right now we're just looking at the horizontal asymptote, and this one is at y equals negative 1. So my limit statement for the left will say the limit as x approaches negative infinity, f of x equals negative 1. For the right, the limit as x approaches positive infinity, f of x equals negative 1. Okay? So if you have the horizontal asymptote, that is the value of your limit statements for the left and the right side. So graphically, it's pretty easy. Okay, let's review slant asymptotes again. If the degree of the numerator is exactly 1 greater than the degree of the denominator, a rational function will have a slant asymptote that is parallel to the ratio of the leading terms. Okay, so remember that slant asymptotes only happens with bottom when it's bigger on top and when there is no horizontal asymptote. For Bobo and EATS-DC, you have a horizontal asymptote. The only time you have a slant asymptote is if you're bigger on the top and if the numerator is exactly 1 bigger than the degree of the denominator. Okay? So example 3, which of the following rational functions has a slant asymptote parallel to the line y equals 1/2 times x? Okay, I know that slant asymptotes only occur with bigger on top cases. So what I'm going to do is go through here and figure out if they're Bobo, Botan, or each DC. Okay, so we have x squared plus 3x to the power of 0 divided by 2x squared plus x to the power of 1 plus 6 times x to the power of 0. The leading term is x squared and 2x squared in the denominator. If I look at the degrees, they are both degree 2. So this one is each DC. Okay, this one has a horizontal asymptote, and the equation is that y equals 1/2, because what you do there is divide the coefficients. So equation 1 cannot be the answer, so I'm going to eliminate A and D, which include 1 as an option. Okay, that one does not have a slant asymptote, it has a horizontal asymptote. Okay, for equation 2, we have x squared plus 4x to the power of 1 plus 1 times x to the power of 0 divided by 2x cubed plus x squared plus 2 times x to the power of 0. The leading term is x squared in the numerator and 2x cubed in the denominator. If I look at the exponents, I have 2 in the numerator, 3 in the denominator. It is bigger on the bottom. This one does have a horizontal asymptote, and it is at y equals 0. So equation 2 can also be eliminated. Okay, let's look at equation 3. X squared plus 3x to the power of 1 plus 2 times x to the power of 0 divided by 2x to the power of 1 plus 4x to the power of 0. The leading term would be x squared in the numerator and 2x in the denominator. If you look at the degrees, we have a 2 in the numerator, which is bigger than the degree of the denominator, so this will be Botan. That means that there is no horizontal asymptote. Now, to determine if you have a slant asymptote, you need to subtract the exponents, and if it is exactly 1, then there is a slant. So 2 minus 1 does equal 1, so yes, this one has a slant asymptote. Okay, so 3 is a contender right now. Let's see if 4 is or is not. Okay, we have x to the power 4 plus x cubed plus 5x to the power of 0 divided by 2x squared plus x to the power of 1 minus 1x to the power of 0. The leading term would be x to the power of 4 and 2x squared. Okay, 4 is bigger than 2, so this is Botan. This one also does not have a horizontal asymptote. Let's see if it has a slant asymptote by subtracting the exponents. 4 minus 2 is 2, so this one does not have a slant asymptote. No slant asymptote and no horizontal asymptote. Okay, so 4 is eliminated from the running, making C the only answer. So only equation 3 had a slant asymptote. Okay. And if we wanted to do this one all the way, remember it's when you divide the coefficient. So we have 1 here. So this would be approaching y equals, you divide the coefficient, which is 1/2, and then you subtract the exponents 2 minus 1. So this would be 1/2 times x, and then 2 minus 1 is just 1. So these are the same. Okay, so that's why 3 is the only answer there. I'm going to do some problems from the homework because they're a little bit different. I want to look at 5 and 6 because in the notes, we didn't have anything that was in factored form. Everything was in standard form. Okay, so you could take the time to multiply all of this using FOIL or the box method, but you really only need the leading term. So a little shortcut to avoid multiplying everything out is to just multiply the leading term of each individual factor in the numerator and the denominator separately, and that'll give you the leading term that you need to determine if it's Bobo, Botan, or each DC. Okay, so if you look at the term 2x, the factor 2x minus 1, remember there's an imaginary x to the power of 0 here. So of these two, this one is raised to the power of 1, the 2x would be bigger. Okay, here we have 5x to the power of 1 plus 6 times x to the power of 0. So this one would be the leading term. For the denominator, we have x to the power of 1 plus 3x to the power of 0, and then x to the power of 1 minus 6x to the power of 0. So the leading term would be x and x. So what you're going to do for the numerator is multiply 2x times 5x, which is 10x squared, and in the denominator, x times x, which is x squared. Then you're going to look at your degrees. They are both degree 2, which means that this is each DC, which means that yes, there is a horizontal asymptote, and the equation would be at y equals, and you would divide the coefficient. So the coefficient of the numerator is 10, and the denominator, there is an imaginary 1 there, so it would be 10 over 1. Okay, so the equation would simplify to just y equals 10. Okay, let's try that again with the question 6. So inside, the leading term would be x squared, but I see that this factor is being squared. Anytime I square something, I know that I'm multiplying it by itself. So I know this will be x squared times x squared, which is x to the power of 4. And then in the denominator, my leading term is 3x cubed. If I look at my exponents, I have 4 in the numerator, 3 in the denominator. So I know that this will be bought in. It is bigger on top. That means no, there is no horizontal asymptote. So I don't have to write anything in the line below that. Okay, let's try another one. X minus 2, the leading term would be x. And the second term, negative x, would be the leading term. Make sure that you take the negative with you. Okay, in the denominator, we have x, and this one is being squared. So this gives me x times negative x, which is negative x squared. And here we have x times x, which is x squared. Okay, my degrees are both 2, so I know that this is going to be each DC, which means that yes, there is a horizontal asymptote, and the equation would be the division of the coefficient. So the numerator had a coefficient of -1, the denominator had a coefficient of +1, so that reduces to y equals -1. Okay, let's do another one. Here we have the leading term is 2x squared, and that's being squared, and then in the second factor we have another x. In the bottom, we have x squared is the leading term and x in the second factor. So 2x squared is being squared. So I'm going to multiply it by itself, and then I have another x in there. Okay? So we have 4x to the power of 5, and then we have x squared times x, which would be x cubed. Okay? So the degree is 5 in the numerator, 3 in the denominator. This will be bought in. Bigger on top, there is no horizontal asymptote there. Okay, and then you can try the rest of them by yourself. On the back page, it does say to find the limit statement, but this is not asking you for both the left and the right limit statement. It is only asking you for one side. So remember that another way to say input values is your x values. Okay, and then decrease without bound means negative infinity. So that means that x is approaching negative infinity. That means you're going to the left on this side. So you're not going to do both the left and the right. They're only asking you to do the left side. Okay, let's do an example here. Here we have the input values, which is x. Increases without bound is positive infinity. So that means that we're going to the right. Okay, so on this, you're going to ignore everything on the left and everything in the middle. And you see how this one has a slant asymptote and it's going up. That means that the right side is going up to positive infinity. So this one, I'm going to write the limit as x approaches positive infinity. The graph of h of x is also approaching positive infinity, right? So as we went all the way to the right, this graph goes up to positive infinity. Let's look at 16. The input values x is approaching, and then it decreases without bounds, so that's going to negative infinity, which is the left side. Okay, you're going to ignore everything in the middle and on the right. As you go all the way to the left, I see my y values are going up, so this will say the limit as x approaches negative infinity, k of x equals positive infinity. Okay, so as we went to the left, the y values go up. Okay, so that's all I have for you today. If you guys have any other questions, please let me know in the comments below. and I will see you in the next video. Bye.